Hi everybody, it's Dr. Pusey here. Welcome to my tutorial video for the 2022 WACE physics exam. Okay, so in question 1 you've been given the wavelength of light, the work function of the material, and it's asking for the maximum speed of the electrons ejected. So you'd start off with the obvious equation, which is equal to HF, subtract the work function, and then I'm going to sub in, instead of HF, I'm going to have HC on lambda, because I've been given the wavelength, the work function, and then I just sub in. And then I'm going to convert that work function into joules, so it's 2.3 electron volts, so that's times 1.6 times 10 to the negative 19. And I get 2.153 times 10 to the negative 19 joules. Now what I want to do is convert this energy into the velocity of the electrons. So the rearranged version of the kinetic energy equation looks like this. And now I just sub in. And once I've done that, I end up getting 6.87 times 10 to the 5 meters per second. All right. Question 2 is a nice and easy one. You've got a seesaw with Patrick on the left and Daksh on the right. The only complication is that the pivot is not in the middle, which means you now need to include the center of mass of the beam itself, which is acting 1 meter from the pivot point. So you just start off with your equations that the sum of the anti-clockwise torques is equal to the sum of the clockwise torques. And then if you want to break that down, you've got an RF from Patrick is going to be equal to the RF from the beam plus the RF from Daksh. So when I sub those values in, I know the radius that Patrick is at, which is 3 meters. His mass, I don't know. I'm going to put in the 9.8, but I'll show you later why it's not really required. And then for the beam, I know it's acting at 1 meter. The mass is 15 and 9.8. And Daksh is acting at 5, 60, 9.8. And immediately you notice that these 9.8s will all cancel out. And I just get m by itself by having 15 plus over here 300 over the 3, and end up with 315 over 3, and the mass ends up being 105 kilograms. There you are. Okay, my explanation of question 3 is very similar to the one in the marking key. I'm doing it from the perspective of each side of a coil, which is moving up or down relative to the flux, which is running across the page. You could also talk about it in terms of the change in flux experienced by the coil, but I think it's far easier to explain how an alternating current is produced if you're referring to each side of the coil moving up and then down, thus creating an alternating current being induced. So I'll start by saying that as the coil rotates, each side travels up or down relative to the flux, cutting through the external flux lines. Then you can say the current is induced on each side, and that reverses every half turn as the relative movement changes. And then I would say that each side of the coil is attached to a slip ring, which maintains contact with each side of the load using carbon brushes. It's important that you mention those bits because they're in the diagram. And then just one more sort of connection statement to say, thus the current through the load will alternate, or something like that, because it's got to, if each side is maintaining the connection to the side of the load using a slip ring, then the current through the entire circuit will also alternate. Cool, there we go. Alright, and question 4 is a mass spec question where you've got a charged particle that's moving in from the left at the bottom, and then it's doing a semicircle and then returning at the detector at the top. Now it's giving you this distance here to the detector. Now if this thing's moving in a circle, then that would mean that 9.14 centimeters was the diameter of that circle. So immediately you should identify that you want to change that to the radius of that circle as being 4.57 centimeters. That's going to help out immediately later on. It gives you all the other information like the B's and the V's and the Q's. And so it's just a matter of identifying that it's a mass spec question. So something like that would be fine. And then mv squared on r equals qvb. Now there's a formula in the data booklet that derives this already, so there's no need to do this if you don't want to. And then you just get that back VB, and that's going to be on V squared R, and that's going to be QB on V. So this is where you want to end up with this equation, and then you just plug in your values. 1.6 times 10 to the negative 19. Your B is 0.350 times 10 to the negative 3. And your radius is 4.57 centimeters. And that is going to be all over the top of the velocity of 2.81 times 10 to the 6. And what you should get is 9.11 times 10 to the negative 31 kilograms. And the great thing about this is that it's a number that looks very similar to the mass of an electron, so you definitely know you're on the right track. And that bleeds into the second part of the question here, asking, which of the following could the particle be? Circle your answer. So with that mass, it's either going to be the electron or the positron. So it's a matter of figuring out what the charge is. So if you look back at the top, you can see that it starts here from the left going through, and now the centripetal force is going to be having to push inwards. So if you want a force that's pointing in towards that way, then your thumb would have to show the trajectory of the particle, which means that it must be a positively charged particle. So it would be D for positron. Okay, in question 5, we've got the induction across the wingspan of an aircraft that's moving with the flux that's coming in at an angle to the wing. So there's a couple of steps here in order to understand it and to solve it. The first one's an easy one. It's to convert the velocity from kilometers per hour into meters per second. And you should get a nice round number of 200 meters per second. That's the easy one. The next one is now to work out the perpendicular component of this magnetic flux density to the wing. To show you what that looks like on a diagram, if I draw the magnetic flux density cutting in like this, and I draw, say, the length of the wing, which is going to be acting horizontal, then what I'm actually searching for is this vertical component, because this vertical component is perpendicular to the length. Now I've been given this angle here as 33 degrees, which means that this vertical component here becomes, so B ends up being, well, the perpendicular component of the magnetic flux density is B cos 33. So now I can go ahead and solve the problem. So I know that the EMF, is equal to LVB perpendicular, which ends up becoming LVB cos 33. And I go ahead and solve for all the pieces. Cos 33, and that ends up being equal to 0.4898, which to three significant figures is 0.490 volts. And that's the first part. The second part of the question is a single mark answer, but it's giving you these values here, and immediately you can see that something's up. If it's only worth 1 mark, it should be a pretty straightforward response, but it looks like it's making it out that you might need to do a calculation. That's not the case. If you have a look at what it's actually saying is, if you come across and you decide to connect an ammeter from here like so, what would the current passing through this ammeter be? But remember, the ammeter is also going through the magnetic flux, right? So which means that the EMF across the wires and the ammeter itself will be the same as the EMF across the wings, which means you're not going to create a circuit of flowing current. The EMF is still going to be in one direction, either to the left or the right. So what I'm essentially saying is, well, that means that you're not going to experience any current going through here. So your answer should be 0. And when you see that it's only worth 1 mark, you can sort of think, oh yeah, okay, yeah, that makes sense now, because it's actually not a calculation that's required. All right, question 6, you're looking at the centripetal forces here acting on 2 coins. You've got a coin there, coin 1 and coin 2. They're both on a disc, and as it spins, eventually coin 2 is the first one to leave. And you'd expect that's because it's traveling at a higher velocity, which means it requires more frictional force, or more centripetal force, which comes from friction, in order to keep it going in that circle. So you'd expect coin 2 to come off first. Now what the question is telling you is that occurs when the frequency is 2 Hertz, and it's saying, okay, well, if we keep spinning it, when will coin 1 require too much force which can be provided by friction. So the first thing that we want to do is actually figure out, okay, well, what is the maximum amount of friction that these coins will experience due to the plate. Now, the good thing is that they both have the same mass and they're both the same size. They're identical, which means that's going to be the same for both of them. So I'll start by setting it out and saying that for 2 Hertz, the centripetal force is going to be equal to the maximum friction, right? And that centripetal force is going to be, I've already got there for 2 Hertz. So what that means is the maximum friction before the coin starts to slide is going to be equal to mv squared on r, and then I want to get v in terms of f, so I'm just going to go ahead and put m, and instead of v it's 2 pi r on t, but I'm going to put the f there instead because obviously I want frequency, and then come across to r. And I'll just keep working that through, and what I'll end up with is, I like to put the numbers at the front, 4m, then pi squared, and then r, one of them cancel there, so keep r by itself, and then f squared. And now I can just sub in, right, so I've got the 1.2 there, which is for coin 2 over here. And then when I put that in, that ends up being 4.74 newtons. Now that is the amount of friction that can be provided just because of the weight of the coin on top of the turntable. That's not going to change because the coins are identical, and you assume the turntable's sort of made of the same sort of stuff. It's uniform throughout. So what I'm saying is that is the constant. Now, if that's a constant, what I need to do now is just find the frequency for when r is going to be equal to 0.3. So I rearrange the equation above, and I end up looks like this, 4.74. And then I just divide it by all these bits at the top here, except instead of 1.2, I put in 0.3. And if you do that, you end up getting 16.00 something, which is a good sign because that means it's a nice round number. And if that's what f squared is equal to, that means that your frequency is going to be 4.00 hertz. And there you go. Question 7 is a more conceptual one where you've got a sort of a conductive bar here where the current is going to be traveling around this way and then going from B to A, so sort of into the page. So if you've got the current going into the page, that's the direction of your thumb, and you've got the field that goes from north to south, so downwards, then what you'll end up is a palm that is facing to the left. So for the first question, it's asking for the initial direction of the bar, that would be to the left. And then the question asks, explain why the bar moved. There's lots of different ways you can approach this, but I would start by talking about how moving charges in the bar, or current in the bar, will create a magnetic field, and that if the current's going into the page, then that magnetic field will be clockwise. Then I'll talk about how the bar is inside an external magnetic field that's generated or created by the magnet, by the permanent magnet, and that's going to be a downward magnetic field. And then finally how those two fields would interact with each other, and then you'd have a force being experienced by both the bar and the magnet. But it's all talking about the bar, so you'd say the bar is going to the left. And you can also talk about this, just saying that if you have a current carrying conductor inside a magnetic field, it'll experience a force, and that's another way that you could have answered this question. All right, question 8 is a gravitational force question by the looks of things. So what you've got is two spheres are separated by 10 meters, but then remember when you're working out the force, you want it between the center of mass. So that distance is actually going to be 10 meters plus half of that, which makes it 12 meters. So you just put that into your equation. So the gravitational force is equal to G m1 m2 over r squared. And then you sub in those values. Notice that they're both 12.5 because they're identical. And what you should end up with is about 7.237 times 10 to the negative 11. So put that down here. There's a lot of space for it. 7.24 times 10 to the negative 11. Where this question gets a bit tricky is when you start looking at what's happening afterwards. So now it's saying, what does the force look like as the two spheres get further and further apart? So if you look at this graph, it's a separation of centers. So basically what you've done already is D. And you've got here, that was about 7.24. So up here, you're looking at about here, so 7.24. So putting that in there doesn't give you any extra marks, but it's a good little starting point. Now, the next thing you want to know is what happens to that gravitational force if you double the distance. Now, you know that this is an inverse square law because it's proportional to r squared, 1 and r squared. So what I would do is I would just say, well, at this point, it's going to be 7.24 divided by 2 squared. And what you should get is about 1.81, so around here. And you should get 1.81 times 10 to the negative 11. So the question says that you need to indicate the magnitude of those forces with a number. You can either do it here or you can go on here to the y-axis. It doesn't really matter. And then for the 3D, it's going to be 7.24 over 3 squared. And what you should end up with is, I think it was like 0.8, but it doesn't actually ask you to work out what it is for 4D, but if you were going to do it, it'll be about here. And then for 4D, it's going to be 7.24 over 4 squared. And you'll end up with 0.45. So you're looking at something about here. And again, you need to specify what that value is so that the marker knows that you've calculated it. You're not just guessing like that. Right, and then what you need to do is show that it's a curve. So rather than draw sort of a straight line between these points, you want to show a curve. I'm going to try to do it on the computer. It's going to look pretty rubbish, but let's see what happens. Nice, flowy curve. Wasn't very good. Let's try again. Nice and easy. Nah, still no good. Nah, try again. There, that'll work. Okay, cool. So something like that, indicating the numbers, because it's 4 marks, right? So you want to have cut the calculated points, showing the curve, and all that sort of good stuff. All right, so question 9, you've got 2 parallel plates here. One's got a positive potential, one's got a negative potential. It's telling you the potential difference is 10 volts, which is what you'd expect between these two. Because this is positively charged, it's negatively charged, you have an electric field that's sort of going to look like this between the plates, and that should give you a hint as to what's going on. The electron actually sort of starts here in the question and then moves across like so. And as it does so, you'd expect that if it's going towards a negatively charged plate, it's actually going to be repelled by the plate. So although it doesn't actually move away from the plate, it will slow down. And that's the key here, knowing that this electron is going to slow down or lose energy. So to work that out mathematically, you want to say that the kinetic energy is lost, and that's going to be equal to the work done by the field. So you can just write it as QV if you like, but it's just going to be 10, because it's 10 volts and the charge is E, so it ends up being 10 eV. So that's how much energy is lost by the electron as it goes through. So we can just represent that as 10 times that number, so 1.6 times 10 to the negative 18 joules. And now we've got it in joules, we can then say, okay, well, if you remember this equation from the previous question, 2E on M, and you sub those values in, and you end up with 1.87 times 10 to the 6 meters per second. Okay, so we're nearly there. Now you need to work out the de Broglie wavelength. So that's from your formula sheet, sub in MV, and put the values in. Right, and what you should get is 3.89 times 10 to the negative 10 meters for your wavelength. Okay, so question 10 is an interesting one because it gives you more information than you need to solve the first part of the problem, and then you use the extra information to solve the second part of the problem. But the issue with that is that that means that you can approach this question in a number of different ways. I'll show you the 2 main methods, and what you'll also notice is that because the information they've given you lacks precision, you'll find that if you do it one particular way, you're probably not going to get a result that gives you much confidence, and I'll talk about that in a moment. So the first question is asking what angle must a shooter fire the arrow for it to hit the center of the target. And this is another issue that I have with this question, is I don't really think it's clear in the question, but essentially what it says is that the launcher aims for this spot here, while it's facing this spot here, it fires it, and then it lands when it's facing 45 degrees. And I don't really think that's clear in the question, but what that means is that the flight time is going to be however long it takes to make that turn. And it gives you enough information in the question because it tells you that it takes 32 seconds to make a full revolution. So you get that 32 seconds and you multiply it by the 45 degrees over 360 of total, and then what you'll end up with is 4 seconds. So that's your flight time there, and that could be the hardest part to find out if you haven't really got this information. And what you might find is some of you might have instead used the extra information that was given in both vertical and horizontal components to solve to get around 4 seconds, but everything becomes much more harder that way. Anyway, so there's 2 main pathways you can go from here. One is to solve using the vertical components, and one is to solve using the horizontal components. So if you were to do it vertically, what you'll end up with is S equals U, S equals UT plus half AT squared, because you need to factor in the gravitational acceleration. And it gives you the S as negative 30. The U ends up being 50 sine theta. and then you're going to subtract, oh, don't forget the t of 4, and then you subtract the 4.9 t squared. And of course, that's going to be multiplied by 4 squared. It looks a bit messy that way. Anyway, what you'll do if you resolve that, you should get 78.4. So what I've done is I've pulled this value over here. I subtract 30, and that's going to be equal to 200 sine theta. And then I can start simplifying it. Sine theta is going to be equal to 0.242. Therefore, theta ends up being 14 degrees. And that's a nice round number, which looks good. And that's what they have in the marking key. Now, you might have done it using the horizontal components, which is actually what I did when I first did this question. And now you've got S equals UT. Nice and easy. And 195 is going to be equal to 50 cos theta multiplied by that 4. And if you simplify that, you get cos theta is equal to 195 over 200, which ends up being 12.8 degrees. Now notice that they're different, right? So you got 14.0 and 12.8. So the acceptable answers would have been 14.0 or 12.8, depending on how you answered or what method you took. Both would have been acceptable. But you can see straight away that there is an issue with the question if those two values don't even really come close. So then the next part of the question is saying, well, now we want you to use a calculation to confirm that the arrow hits the target. And that's where you need to use the extra information that you've been given. So if you've done it using the vertical method, you need to solve the horizontal components with the data that you've got now. And if you did it using the horizontal method, solve it using the vertical components that you had. So what that looks like, you come down here with the vertical, you should then start working with the horizontal information. So S equals UT, which is equal to U cos theta times T, and then you sub in your values. And what you'll end up with is 194 meters. Now, in the question, it says that the distance is 195 meters. So horizontally, you've got this result. I think it said it's also 4 meters wide or something. I can't remember. So you can say, yep, that's approximately 195 meters. So it will hit the target, which is great. Now, but what if you did it using the horizontal method? Well, now you solve it using the vertical components. So you sub it in, put in your values, and you end up getting a vertical displacement of negative 34.1 meters. Now, when I did this and I got that value, I didn't really think it was close enough to 30 meters, because that's what it should be, right? And so that distance there is 30 meters. So when I got this data, I thought I made a mistake, but it wasn't that I made a mistake. It's that the question, the data in the question didn't actually fit itself. So if you did it using this method, which is the method that I used when I first did the question, you would have been given full marks for your answer, because it's not your fault, or it wasn't our fault that this is a problem. But in the marking key, you'll see they use this method. There's no reason why this method on the left-hand side is better than the right-hand side. In fact, I would say the one on the right-hand side is probably easy to start with because you're only dealing with the horizontal components. So it's a bit annoying, but one thing I can tell you is that even if you said it was negative 34.1 meters and it wouldn't hit because it wasn't close enough to 30 meters, you still would have been given the full marks. Obviously, they'll be lenient in how that's marked. Okay, question 11, the last one of the short answer section. You've got a special relativity scenario where you've got two people, each in their own reference frame with a 1 meter ruler, and one is moving past the other at a velocity of 0.8 c. And the first question is the easy one. What is the length contracted length of the ruler? So you got your equation that you've already been given, proper length multiplied by 1 take v squared on c squared. And you sub in your values, 1 meter ruler, 0.8 c, and what you should end up getting is 0.6 meters. And the second part of the question is, okay, what does the other reference frame measure the other ruler to be? They're equivalent frames, so that's going to be the same answer. And the other hint with this one is that it tells you it's worth 1 mark, which means you shouldn't be expected to do a calculation. Where it gets tricky is this part C here. It's asking you to explain that, if one person's measuring the other as 0.6, and, that means they're measuring it to be smaller, and the other person gets the exact same sort of result. Can you explain that? The answer key goes pretty far into depth, which was surprising to me. Started talking about simultaneity and that sort of stuff. So I would start by talking about how both observers will see each other as having a velocity relative to one another. and therefore you'd have length contraction observed by both observers as they're looking at a moving ruler. And then you would need to talk about simultaneity in some way. I think the best way is just to be pretty vague about it and say this is possible due to the lack of simultaneity between reference frames. How much detail you need to know is unclear in the syllabus. This question was a bit of a stretch. If you look at the explanation in the marking key, you can see it's a fairly long one and probably wouldn't fit on the lines they've given you. So I imagine there was a bit of flexibility in the marking key here. But yeah, that's the end of section 1. All right, question 12, we've got a static equilibrium scenario where we've got 2 support pillars either side of a plank, which is hanging from a chain. And then the first part of the question, they're saying if we have a person who's sitting at point A, it gives you the information and it's asking what will the tension in each chain be. And that is a pretty easy one to start with. So what I'm going to do is start by putting in a free body diagram. You've got a mass here of mg. Now there's going to be 2 mg's there. You've got someone sitting on it, and you've also got the plank itself, and then you're going to have a tension in the chain here and a tension from the chain here. So now what I'll do is I'll put that in my equation, starting with the assumption that all the forces acting up are going to be equal to all the forces acting down. So breaking that down, I'm going to have the tension from chain 1. Now notice that it's acting at an angle of 30 degrees. Now if I want to know what the vertical component of that force is, then that's going to be the cos of 30. So T1 cos 30, and one for the other side as well. So T2 cos 30. And both of those will be handling the mass of the plank times G plus the mass of the father times G. And now if I sub those values in, knowing that the tension in each chain must be equal, because notice that they're acting at the same angle and the person who's standing on it is right in the middle. So I can just simplify that down to having 2 of T cos 30, and that's going to be equal to 9.8 plus 80. Right. And then I break that down further and end up getting just T is equal to 103.6 over 2 cos 30. I imagine one of the most common mistakes will be forgetting about the plank. If you sub that in, what you should get is 464 newtons. Okay, and the next part is to work out the horizontal component of the tension in each chain. Now what we've just solved already is we've solved for the actual tension in the whole, or the whole tension in the chain. So what I'm going to do now is I want to resolve this part here, the horizontal component. So if I was to sort of illustrate that in a diagram, it would look a bit like, you got your 464 here, and I need to solve for this part here. That's the tension I'm trying to solve, and that's just going to be equal to TH, knowing that this angle here is 30 degrees. It's going to be equal to 464, which is what we've calculated above, multiplied by sine of 30, and that should be equal to 232, half that. Right, so now part C is where things start getting a bit complicated. What the question's asking is to confirm that the supports do tip over when the father sits on the plank. So it's telling you what happens. You need to use some maths and some physics to sort of prove that that's the case. So because I don't want to have to keep on flicking back and forth between the diagram, what I'm going to do is just draw one side where you've got the support here and the center of mass acts down, and we also know these dimensions, and we also have the chain which is acting like so. So we've got 2 forces acting on it. The green one here, which is a tension force, we've already calculated that as 464 newtons, and we know that it's acting at an angle of 30. And we could use the data from the previous section actually, if we wanted to. Okay, so what's going to happen is there's going to be a point here where the support would pivot. And if this tension of force is too large, then it will overcome the rotational moment provided by the support itself, so it will start to tip over. And they're saying that will happen, but we need to show that will happen. So what I'm going to do first is actually work out, okay, what is the maximum amount of rotational moment, or what is the maximum torque that this support can provide based purely on this mass here. So I would say, okay, well, the moment from the support is going to be equal to RF. Now, the good thing is that I can say that this force is acting perpendicular to the pivot at 0.4 meters, and the force is mg, which is going to end up being 70 times 9.8. And I get 274 Newton meters. So that's how much torque the support can actually counteract if that's what's been produced by the tension in the chain. So let's work out what the chain is actually doing. The chain is pulling at 464 at 30 degrees. Again, you could use information from the previous part if you like, but I'll just do it anyway. RF sine theta, which ends up being 1.5 because it's acting up here, 1.5. The tension in the string or chain is 464, and that's acting at an angle of 30 degrees to the arm. Oh, what am I doing? And what you'll end up with is 348 Newton meters. So we can see straight away that this is larger than this. And now I just need some sort of statement that sort of points that out. So I'm going to say 348 Newton meters is larger than 274 Newton meters. Therefore, support will tip over, and that should do. And finally, it's asking, without using any calculations, describe how the tension in each chain will be affected if someone moved. They're lighter now, so you're not going to have any supports falling over. But what happens to the chains as someone moves from here all the way over here? And common sense will prevail here. You'd expect that if someone's moving from this location to this location over here at B, then B would start to experience a higher tension, and as you would also expect, the tension in this chain over here would decrease. So I would say that chain 1 would decrease and chain 2 increases. And there we are. Okay, so for question 13, we've got a photon that collides with a stationary electron, and then it looks like it rebounds. And you can see that as it comes in, it has a certain wavelength, and then the electron starts moving, which means it gains kinetic energy, and the photon will recoil with a higher wavelength, and that's part of the question later on. So let's start with the easy questions. The first part is saying, what is the original energy of the photon in electron volts? That's a nice one to start with. You go E equals HF, and then you have wavelength, so there we are, and then you just sub in the values. And that's going to be over the wavelength it was when it was incident. And what you should get is about 2.825 times 10 to the negative 15 joules. You can divide that value by 1.6 times 10 to the negative 19, and you should get 17658 electron volts. So down here to 3 sig figs, 1.77 times 10 to the 4 electron volts. And the next part is asking for the momentum of the photon before the collision. So this is another easy one, where you have the wavelength is equal to H on P, rearrange, and substitute. And you should get 9.42 times 10 to the negative 24. Right, there we go. So let's move on to part C, where you need to explain why the wavelength of the photon is greater after the collision. Okay, so I've broken it down into 4 points. The first thing to point out is that the energy is transferred from the photon to the electron. And because of that, the photon has less energy after the collision. And then you want to point out the relationship that energy is inversely proportional to the wavelength. So a decrease in energy yields an increase in wavelength. Okay, so now let's get to the big one, the 6-mark question. It's asking to calculate the speed of the electron after the collision. So now you're going to be using the value of the wavelength after the collision to solve the rest of this. So start with what you worked out in the very beginning. We worked out the initial energy of the photon. And remember, this is the photon we're talking about here, not the electron yet. So now we want to work out what the final energy of the photon is when it rebounds, using the same method as we did for the first part of the question. And you end up getting 2.643 times 10 to the negative 15. And notice that I'm keeping an extra significant figure here. And that's deliberate because I notice that I'm going to be subtracting one from the other. And if they both start with the number 2, then that's going to be lost. So I'm going to have 3 significant figures left. So it's good practice to do this if you're dealing with large numbers in general until you do the final answer. Just keep at least one more significant figure there. So that's the photon going from this amount of energy to this amount of energy. What I'm going to do now is work out the energy difference, or essentially the change in energy that the photon encounters. And that's going to be this value, this value subtract this value, and you should get 1.82 times 10 to the negative 16 joules. And then you need to remember that that energy is what goes into the kinetic energy of the electron. And now we can just go back to our equation that we're pretty familiar with right by now. I think this is the 3rd time we've used it so far in this exam, to work out the velocity of that electron. And I got 1.999 times 10 to the 7, which rounds out nicely to 2.00 times 10 to the 7 meters per second. All right, and that's done. Question 14 is a decay, what you'd see in a beta decay, where you have a neutron decaying to a proton, electron, and an antineutrino. The part A is probably, arguably, the easiest 6 marks in the exam, because it's something that you can pick up off your formula sheet, and if you've done enough of these problems, you should be able to answer these without the use of a formula sheet. If you've got a neutron, that's going to have baryons in it, so it's going to be 1. A proton is also going to have baryons in it, so it's going to have a 1. Electron and the anti-electron neutrino are going to have 0 and 0, but they will have lepton numbers. So 0 and 0 for lepton numbers for the neutron and the proton. There's no quarks there, but the electron and the antineutrino, that's where things, I guess, could get a little bit hard. The electron has a lepton number of 1, and because it's antimatter, the electron antineutrino has a lepton number of -1. Part B, it tells you the mass of the neutron, and then it's telling you what the mass of the proton and the electron is, and it's saying to assume that the antineutrino has 0 energy, so you could say that has a 0 mass essentially. So what you would come along with is to say, well, let's first work out what the mass of the left hand side is, and that's easy. That's just the 1.675 times 10 to the -27. That's your neutron. And now the mass of the right hand side, that contains a proton and a electron. And now at this point, you've got yourself a number that looks very close to the one at the top, which is what you'd expect. And you have very little mass difference that you can see already. And it's really important that you keep all the precision in this number, because you can see that the 1.67, that's the same between these two numbers here. So what's left afterwards is really important. So you want to keep that to maintain precision in the problem. So when you work out the change in mass, or the mass difference, I suppose, you should get 1.0891 times 10 to the -30. And that's just this number, subtract this number, and you'll get a negative number, which is just showing you that the mass is lost. Okay, so great, you've got all this stuff, and now I'm going to convert this mass difference into energy like you would in year 11, and it ends up just being mc squared. Don't forget to square the c, and what you get is 9.80-ish times 10 to the power of -14 joules, and the question's asking for that number in kilo electron volts. So there's actually 2 marks in that. One is to go from joules to electron volts, but divided by 1.6 times 10 to the -19. And this is what I got. And that's what it is in EV, but again, it's asking for kiloelectron volts, so you come across to here, and you'll end up with 613 kiloelectron volts. Okay, so part C, if the electron accounts for 90% of that kinetic energy, calculate the velocity of the proton. So it's a little bit tricky in the wording there, but what that means is that 10% of the above energy is given to the proton. And if that's the case, that means the proton's energy is going to be the 9.8 times 10 to the -15 joules. So I'm going to do it in joules because you're going to use everyone's favorite equation again, V equals 2E on m, except in this case, m is going to be the mass of a proton. And you should get 3.42 times 10 to the 6 meters per second. Now, if you use the relativistic version of the equation, you get the same answer. If you got an answer here where this speed is greater or even getting close to the speed of light, that's when you want to start thinking of using the relativistic equation. But in this case, the estimate that we use here is just fine. Anyway, so you divide this by 3 times 10 to the 8 to get what it is in terms of C, and you should get 0.0114 C. There we are. So question 15 is your graphing question for this exam. You've got a question that's some information about energy transitions for hydrogen, and you've got a diagram here that's telling you the wavelength of photon that's emitted when you have these transitions occurring. So you're going to use this information to populate this table. So for the first row, it's not too difficult. One thing to watch out for is that you want to keep it to 3 significant figures. That's important because if you don't do that, you're going to lose the mark that's most likely going to be allocated, especially if they tell you how many significant figures to use. Okay, all right, so now I'm sure the next part is to do the graph. Now, the good thing is they've given you the scale here, which makes things much easier. What I'm just going to do now is take my time and set this graph up, and I'll see you when I get to the other end. So you notice at this point that I've got on the y-axis, I've got the 1 on lambda, but I've also included the units, which is important. But because I'm just looking at sort of the reciprocal of the energy transition sort of stuff, there's no units in there. It's dimensionless. So there's no need for units for the x-axis. Okay, so now my data is plotted. I'm going to draw a line of best fit. Okay, so that looks pretty good to me. I can see that I've got some data points that are below the line, some that are above. And yeah, that'll do for now. Okay, so the next part is to use my line of best fit to calculate Rydberg's constant. Now, it doesn't tell you this explicitly by the looks of things, but really what you need to do is find the gradient of this line. So what I'll do is I'll find 2 points. I'm going to find a point on the right-hand side and find a point on the left-hand side of the line of best fit. I need to be very careful. I know it's very tempting to pick this point right here and use the data point, but that is explicitly forbidden, so you should not do that. Here's a point here. I'll use that one there. And I'll also use, let's have a look, this one here. Okay, so now I'll draw my gradient triangle. Great, and now I'm just going to use my read-offs to find the gradient. I'm just going to do it here to make it a bit easier to see. This point over here is 0.95, and the y value is 10.4. This point over here is 0.73, with a y value of 8. So I can put those values in down here. So now that I've got those values sorted, I can come down here and actually answer the question. Well, first find the gradient as part of answering my question. So now that I have the gradient of my graph, how can I relate that to the equation to get Rydberg's constant? So if we come up here to the top where we've got our equation, this one here. So we plotted on the y-axis, we plotted 1 on lambda, and on the x-axis, we plotted this here, right? So that would mean that our m value, or the gradient, is going to be equal to r on hc. So what that means is that the gradient is equal to r on hc. Therefore, r is going to be equal to the gradient multiplied by hc. And now I can put in my values. One thing I do need to remember at this point is that that gradient is 10.9, but for the units of the graph, if you remember, the y-axis was times 10 to the 6. So it'll actually end up being times 10 to the 6. Meters -1, and this is an arbitrary unit, so you just leave it the way it is. So because of that, this ends up becoming times 10 to the 6. Now I can multiply it by hc, and what I get is 2.17 times 10 to the -18. And importantly, it says here to give my answer to 2 significant figures. So down the bottom here, I can say it's 2.2 times 10 to the -18 joules. All right. So the last part of the question then adapts that equation for ions that have 1 electron in their outer shell. And it looks exactly the same in terms of the equation, except now you have this z squared factor where z is the atomic number. And then it also goes ahead and starts giving you this diagram as well. It's a lot of information, takes up a whole page, and then part D actually says, okay, well, if you start graphing this for helium and compare it to what you got for hydrogen, what would you see as being different? Now, the big difference between these two equations is this z squared value. If it was hydrogen, it'd just be, and this z squared becomes 1, so it looks the same. If it was helium, it'll be z equals 2, and z squared equals 4. So what that means is your gradient here is going to be multiplied by this factor of 4. So to be honest with you, the only difference I really wrote down when I first did this exam was that the gradient was 4 times larger. So I'm going to write that one down now, and also just pointing out that hydrogen has a z of 1. So where I was a bit confused myself is I would think that would be sufficient, but they're asking for 2 differences, and it wasn't really clear until I saw the marking key what they were looking for. They actually want us to sort of go further with this gradient, because obviously if the gradient of the graph is going to be 4 times greater, then you're going to end up with a larger spread of energy values, and they actually want you to write that in there. That was the expected answer here. So what they're looking for, they want you to specify that gradient means you're going to end up with a larger range of values in the y-axis, and that's going to be due to the greater differences between the energy levels. And I guess you could also draw that greater difference between energy levels by looking up here at this diagram as well, which might be why this diagram's here. I'm not sure why else they would put that here. But yeah, that was a funny way to end the question, but yeah, apart from that, we're all good. Question 16, you're looking at a power transmission line question. You've got two scenarios to consider. One is where you have the power station that's operating at DC, and the other you have a power station that's operating at AC. Importantly, the voltage provided by each power station is the same, and so is the current. So the first question is asking for the power output of both stations in kilowatts, and it gives you a ton of space, but you really don't need that much space. So the power generated is going to be equal to the voltage multiplied by the current. So that's going to be equal to 480. This is for both of them because they both have the same voltage and the same current. And what you end up with is 48000. Ask for it in kilowatts. So the answer you're looking for is 48.0 and 48.0. And there's your 2-mark question right there. Part B is where it gets pretty interesting. It's telling you the resistance of the transmission lines is 2.19 times 10 to the negative 4 ohms per meter. So that per meter is important. You need to know how long the transmission line is to work out the resistance of that transmission line. Now, if you look at the top, it looks like the transmission line is 10 kilometers long, but the feedback from the examiners is that everyone made this mistake. It's actually going to be 20 kilometers because the power needs to obviously run down this line and return back to the power station. So the length of the transmission line is 20 kilometers. Now, the cost of that mistake in this question was only 1 mark. So if you did everything else fine, you would have still received the vast majority of the marks. So to get this correct, you want to say that the length of the transmission line is 20 kilometers. And if that's the case, that's going to be 20,000 meters. So now your resistance is going to be equal to 2.19 times 10 to the negative 4 times 20,000, and that's going to be equal to 4.38 ohms. Now, if you got 2.19 ohms, that's because you only factored in one length of that line. So now that we have that value, we can work out the efficiencies by first working out the power loss across the line in each case. Now, where these power lines differ is that there is a transformer for the AC line, which means that it steps up the voltage so the current can be reduced to 10 amps, and over here it remains at 100 amps. So let's go have a look at what effect that has. So I'm going to put the DC case over here and the AC case over here. So for DC, what you're going to have is a power loss given by the current squared multiplied by the resistance of the line. So that's going to be 100 squared multiplied by 4.38. And if you do that, you'll get 43800 watts. So that's how much is lost across the line. But remember, at the other end, they're going to receive the remainder. So I'm going to write power received is equal to whatever the power station provides minus the loss, and that's going to be equal to not much at all, 4,200 watts. So remember, it was 48 kilowatts that it outputs, right? So if that's how much is received, that's how, and we know that it output 48 kilowatts, then we need to work out the efficiency just by working out the ratio of those two. So 4,200 over 48,000 times 100, and that is going to be equal to 8.75%. So in other words, 8.75% of the power generated by the station makes it to the homes. And one thing that I'm sure a lot of people missed is that it says here estimate. And by saying estimate, you need to give it to two significant figures or less. So 8.8% is the best answer here. So now I'm going to do the same process with the AC, and the only difference is that the step-up transformer allowed us to reduce the current in the lines by a factor of 10. So it looks like this. So now 10 squared, which means the power loss is reduced by a factor of 100. So the power received is pretty much very close to the original amount generated, which means the efficiency, you get 99.1%, much more efficient. And remember, two significant figures, so 99% efficiency. So there's lots of places you can lose single marks here. So the first one is to use 10 instead of 20, which was very common. And then forgetting the sig figs here was also worth another mark. So if you do everything else and just made those two minor errors, you're still going to get 4 out of the 6 marks. So part C of question 16 asks why laminating the core of a transformer increases its efficiency. So it's worth 3 marks. So the 3 main points that I would pull out would be, first, just pointing out that eddy currents form, and they form due to the changing magnetic flux experienced by the iron core itself. And then you want to talk about how the energy from the current, or the electrical energy, is then lost as heat. So a laminated core separates the iron into electrically isolated segments, right? So you won't be able to have this conductive path for these large eddy currents to flow. So I've said that will reduce the size of the eddy currents produced, and that will reduce the power lost, and that will increase efficiency. And part D asks to explain why transformers require an AC current to function in electricity transmission. The last part of this question, asking you to refer to electricity transmission, is probably a point that a lot of students might have missed. It's easy to talk about why the AC is required, but then you need to refer it back to the transmission of electricity. So I would start by explaining that an alternating current in a coil creates an alternating or changing magnetic field. And then I'll go a little bit extra and say, look, in a DC circuit, the magnetic field is constant, just to show the marker that you know the difference between the two. Then the second point I've made is the changing magnetic flux experienced by the secondary coil will induce an EMF. And then the last mark would be to say, well, that EMF can provide a current through the transmission line, which would then allow us the transmission of electricity. And that's question 16. Okay, now we have question 17, which is the last for this section. You've got a conical pendulum, which is a bob that's sort of doing a horizontal circle at the bottom as it's suspended from a fixed point here at the top. The first part of the question is telling you that the angle between the string and the vertical is going to be 30 degrees as it spins around, and it's asking you to figure out what the tension in this string is going to be. So I like to draw vector diagrams to sort of help me figure out what's going on. So we've got a tension force doing this, and then coming down is we have the weight force, and if it's going in a nice horizontal circle, then the resultant force should look like that, and it will be the centripetal force. You've also been told that this angle here is 30 degrees, so now I'm just going to go ahead and see that cos of that 30 is going to be equal to mg on t. So cos 30 is going to be equal to mg on t. Rearrange, t is equal to mg on cos 30, and sub in, and what I get is 2.89 newtons. It's a nice and easy one. Okay, so now they're keeping the scenario as having the angle is at 30 degrees, but what it's asking for is the radius of the circular path. So I'm going to draw the diagram again. It's going to look very similar, but I'm actually going to draw the spatial dimensions. So I'm going to have 1.2 meters here. There's also going to be a vertical distance, but I don't need that. And then this part of the triangle here ends up being r, which is what you're trying to solve. And again, that angle is 30 degrees. So with the same information, sine of 30 is the opposite over the hypotenuse. So it'll be r over 1.2. So your radius is going to be 1.2 sine 30, which is equal to 0.60 meters. Okay, part C is where things get pretty complicated. So what it's asking for is to work out the new angle between the string and the vertical if the frequency of rotation is doubled. So it tells you in the scenario up here, it wasn't relevant yet, that all of this occurred with a frequency of 0.49 hertz. So what it's saying now is if I double this frequency to 0.98 hertz, what happens to the angle? And the thing is that when you change the angle because you're spinning it faster, you're also going to change the radius. So you can't assume the radius stays the same. You also can't assume the velocity stays the same. So you need to go back to first principles again. So let's just draw that vector diagram, because again, I don't like flicking back and forth. So we have the tension doing this, and then we have mg here, and we have our FC. Okay, so now looking at this diagram, we're looking at this angle here, this theta angle. I know that the weight's going to stay the same, and I also know that the centripetal force, I might be able to work with that because I know the frequency, and that's related to the velocity and all that sort of stuff. So I'm going to actually find an expression of all of this because I need to find this value, and this value is what I've been working with. So if I just start by pointing out that the tan theta is going to be equal to FC on mg, and sub in, right? And then that comes down to v squared on rg. Right, so I'm going to work with that, but what I want to add into this, I'm going to try and do it nice and slowly, is that it gives me the frequency, not the velocity. So instead, I'm going to get the velocity and put it in terms of frequency, which ends up being 2 pi r on t, or times f. So I'm going to use that, and that's where I'm going here. So now I'm going to have 2 pi RF squared. Right, and everything else sort of stays the same. Now I'm going to simplify. Okay, I'm just going to move it a bit. There, so now I've got 4 pi squared RF squared on G. Now the thing is, the R value is something that I don't know, but what I do know is I know the L value of 1.2. So I'm actually going to put in an expression here for R, and that's going to be L sine theta. Right, so that's something we did above. So now I have 4 pi squared. Instead of R, I'm going to have L sine theta, F squared, all on G. Right, now what I'm trying to solve is the theta. So I'm going to pull the sine on the other side. Now the thing about tan on sine theta is I know that tan is actually sine theta over cos theta. Well, I hope that we all know that. If we don't, we're in a bit of strife. So I know that, so that means I can cancel out the sines, and I've ended up with 1 on cos theta. And that is going to be equal to all of the above, 4 pi squared. Yep, good. Right, so now I know that 1 on cos theta is equal to all this stuff. I know all of this stuff. I know the new frequency, I know the new length, I know G. So all I need to do now is find the reciprocal of both sides, and then I end up with this. And get the inverse cos of that, and I end up with 77.6. Very easy to make mistakes along the way. If you forget to square this 0.98, you end up with 77.8, which is very close. You can also make assumptions where you keep R constant or you keep V constant. The marking key says that if you do any of those things where you keep one of those constant, you're making the question easier, which means you can only get a maximum of 3 marks if you get one of those results. But yeah, it's a pretty challenging question. Very, very mathematical. Okay, part D, explain why theta can never equal 90 degrees. In other words, why can't the string be at a perfect horizontal? So I think most of us might have seen a question like this before, if we do any of, say, the Starbar labs. But the best answer for this would be talking about the vertical component of the tension. So I would first say, that the tension needs to provide a horizontal component, which is your centripetal force, and also provide a vertical component. And that's going to counteract or balance the bob's weight, so it doesn't have any sort of vertical acceleration. And an angle of 90 degrees means that there is no vertical component, which is not going to be possible unless you have a bob that is essentially massless or has no weight or no gravity, which is not possible. And that is the end of section 2. Section 3, everyone's favourite section. First question is number 18. It's an article on light-emitting diodes, or LEDs. The first part of the article is about how LEDs work, where you have a P and an N junction, and you have the electrons over here, and essentially what they're going to be doing is taking up space in one of these holes, lowering their energy level, and then emitting a photon of light corresponding to that energy difference. And then it talks about the luminosity of LEDs, how they basically emit energy in the wavelength of visible light, which makes them more effective as light sources. And then it talks about the difference between efficacy and efficiency. We'll get to that stuff later on. So the first question is asking how a PN junction produces visible light. So essentially what it's asking you to do is regurgitate the information here, which explains how the LED works. So I would answer it by first mentioning that the high energy electrons move across the gap from the N layer to the P layer, and then after they cross, the electron is now at a lower energy level in the P layer. The excess energy after the crossing is released as a photon, and why is it visible? The energy difference of the electrons corresponds to the visible wavelengths of light, and I've just put the formula there that also sort of helps cement that information. And question B is asking for us to describe how LEDs and incandescent bulbs are apparently equally efficient. So why can LEDs use less power to achieve the same outcome? And really your discussion needs to talk about efficacy, or essentially how useful that light energy is. So I've started with what the question has asked me to do and make reference to the graphs of intensity versus wavelength. So if we look up here, we can see that for an incandescent bulb, we have all of this energy over here, but this part here is actually fairly useless, right? Because we only want it in the wavelengths that we can see. That's what we want light to do. So an LED, however, focuses its energy sort of in this spot there, which means all of the energy that's been converted from electrical energy is essentially far more useful. So that's how I've answered this question. First, I've said that the graphs show that the LED lights contain the majority of their energy in the visible wavelengths. Then I've said that the incandescent bulbs produce energy mostly outside of the visible range. Therefore, most of the light energy produced by the LED bulb is useful. And since many would say that efficiency is a measure of the useful output as a fraction of input, then the LED provides a greater useful output and is therefore more efficient. So question C is asking us to use the information given in the article to determine the current that's going to be passing through an LED. Now the information in the article is that the wavelength you're looking at is 430 to 505. Might not need this yet. And the forward voltage is 3.60 volts. Now it's saying that the efficacy is 120 lumens per watt. So what that means is that if it's producing 120 lumens per watt and we need to produce 840, so that means that the power we require is going to be 840 over 120, which is going to be equal to 7 watts. So we need 7 watts of power, and we know that power is equal to VI. Rearrange that, and you end up with 1.94 amps. So part D is asking to use a calculation and data to show that the minimum forward voltage for these crystals is large enough to produce photons with the lowest energy required for blue light. So I need to figure out what the lowest energy required for blue light is first. So looking up here, the blue one is 430 to 505 nanometers. So if they're saying blue is 430 to 505 nanometers, it's asking for the lowest energy required for blue light, which means I'm going to focus my efforts on the 505 nanometer range. So first I want to figure out what is the energy of a photon that has a wavelength of 505 nanometers. So I'll write that down, and I end up with 3.94 times 10 to the negative 19 joules. Now this number represents the minimum amount of energy that is going to be required to produce blue light. Now the question's asking to show that if it has the forward voltage up here of 3.6, right, that you'll be able to provide the photon with enough energy to provide at least that 394 times 10 to the negative 19 joules. So if you have a voltage drop of 3.6 volts, you'd work out the energy that corresponds to, and that's going to be equal to VQ. So that's going to be 3.6 times 1.6 times 10 to the negative 19. And you get 5.76 times 10 to the negative 19 joules. So this is the amount of energy that the electron will lose when it drops across 3.6 volts. So you can see that this number is greater than this number, which means you will be able to produce this amount of energy. But the important thing now is just to specify that you know this information. So the 5.76 times 10 to the negative 19 is greater than 3.94 times 10 to the negative 19. So therefore this forward voltage is large enough. There we are. Okay, so question 18, you're looking at a lot of information being given to you in this question, and it's asking you to effectively calculate the mass of coal the world would save per year if lighting was all provided by LEDs. And it gives you a fair bit of information in this article. The wording can be considered a little bit unclear in some sections, but I think the best approach is what I'll do here. So the first thing it tells you that the lighting accounts for 15% of global electricity consumption. So what I'll be doing now is saying, okay, well, if the global energy consumption is 194 EJ, right, or times 10 to the 18 joules, then what I'll do is I'll first work out, okay, how much energy is consumed by the lighting, and that's just going to be 0.15 times that number. And I get 2.91 times 10 to the 19 joules per year. So the next step is now to figure out, okay, well, it's asking how much you save if you make everything LEDs. So it tells you that at the moment 40% is provided by LEDs, which means that 60% must be incandescent bulbs or other types. So what we'll do now is work out how much non-LED lighting is in this energy consumption, and that's going to be 60%. Okay, so now I know how much is used up by non-LED, so this is the potential to change. And then it's the next step I would use at this point is, okay, well, this is how much we can save. This isn't going to be removed, so how much of this amount can we save by switching to LED? Now, if you have a look in the article at the top here, it says A light bulb may use 60 watts of energy. An LED bulb can produce the same amount using less than 10 watts. So if we make the assumption that we're going from 60 to 10 watts, so that's what I'll be doing. So here we are. So I'm saying here that we'll save 50 joules for every 60 joules that we use. So essentially that means that I'll be multiplying that value above by 50 over 60, because remember, this is how much we're saving. 1.455 times 10 to the 19 joules. Okay, so this is how much we're going to be saving by making the switch. But we also need to remember, and it says here, that 80% of the world energy consumption is derived by fossil fuels. So this is how much energy consumption we'll save, but we're looking at how much we save of fossil fuels. So we need to multiply this number by 80%, which is equal to 1.164 times 10 to the 19. So that's how many joules we'll save per year. And now we know how many joules we'll save per year. We want to convert that to a mass of fossil fuels, which up here tells you that 1 ton will give you 21 gigajoules of energy. So I get my energy amount, divide it by that 21 gigajoules, and I get 5.54 times 10 to the 8 tons. And of course, the question does say very clearly estimate, which means that we need to give our answer to 1 to 2 sig figs. And there we go. Okay, now with question 19, the last one for the paper. It's just an article on Kepler's laws, and the concept of barycenter is also introduced there as well. So looking at part A, it's asking to use Kepler's second law to describe the relationship between the distance from the sun for a planet and its orbiting speed. So if we come up to the top here, we've got a little image that has Kepler's second law written on it. And then the information given is that the two shaded areas are equal and cover equal times. That's the important thing, equal times. So if we have a planet that's close to the sun here, then you can see that it travels this much distance in the same amount of time. If it was over here, it would only travel this much distance. So as the distance is further away, the velocity will decrease because it's covering less distance in the same amount of time. And then part 2 of that question is to justify the relationship with the reference to that figure. I would start by pointing out that figure 1 shows 2 paths in the same period of time, and the path that's further from the sun covers less distance. That way you have the areas equal to the same. But that means that if it's covering less distance in the same amount of time, it must have a lower velocity when further away from the sun. So part B of this question is just a derivation of Kepler's third law from first principles, and it's probably something you've done in class already. In the article it says that this is where the centripetal force is equal to the gravitational force, and now you just sub in the formula that you've got. Okay, so now I see straight away that these masses will cancel out, this r will cancel, and we'll lose that squared value. At this point I'm also going to introduce that the velocity is given by 2 pi r on t, and that's given to you in the article as well, except it does it in a sort of weird way. But if you have that, it ends up being on r. Okay, so at this point I can see here that I've got r squared and r. So what I'm going to do is I'm going to put the 4 pi squared over here and put the r over there. That ends up being r cubed over t squared is equal to gm on 4 pi squared. And finally, I need to get it in the way that the data book has it, which is just the reciprocal of both sides. And there we go, 5 marks right there. Question 19c is an interesting one. It wants you to use moments to estimate how far the barycenter is from the center of the Earth. So when I first read this, I was a little bit confused, but I think it's in the article, it tells you here that the system could be seen as a balance beam with the barycenter located where the fulcrum will be placed to achieve equilibrium. And what that means is if I make this the barycenter, and I have Earth having a force that way towards the sun, and I have the moon having a force that way towards the sun, I'm going to go ahead and say this is the Earth and the moon, draw it up a bit neater. So now essentially this R1 is what I need to figure out. This is the distance between the center of the Earth and the actual barycenter, or the fulcrum. So I'm going to write down what I do know, and that is that I know the distance between the Earth and the moon. So I know that R1 plus R2 is equal to 3.84 times 10 to the 8. And I know from here that R2 is going to be equal to 3.84 times 10 to the 8 subtract R1, because I'm going to be subbing that in later on. So now I just use my my moments calculation that RF is equal to RF. So now I'm going to substitute in where R is R1, and the force from this one here is just going to be, I'm going to say the mass, and you'd expect that the acceleration of both of these masses is going to be the same. So I can just keep it in terms of the mass. So R1 ME is equal to R2 MM. And I'm going to sub in the values that I know, And remember, I know that R2 is equal to 3.84 times 10 to the 8 minus R1. So now I'm just going to bring this 7.35 over to the other side. And I'm going to sub in, instead of R2, I'm going to write 3.84 times 10 to the 8 minus R1. So now I'm going to bring this and put it on the other side, so it ends up being 82.2. R1 is equal to 3.84 times 10 to the 8, which means R1 is going to be equal 4.67 times 10 to the 6. And it is saying estimate. So I'm going to give it to two significant figures, 4.7 times 10 to the 6 meters. And there we go. Okay, lucky last question is to show that the moon is traveling roughly 81 times faster than the Earth as they orbit the barycenter. So remember, looking up here, you've got the Earth at this distance R1 and the moon at this distance R2. I'm going to rewrite these as RE for the radius of the Earth about the barycenter is going to be 4.67 times 10 to the 6 meters. That's what I've just worked out over here. And then the moon, I haven't done that yet, is this distance here, the distance from the moon to the barycenter. That's going to be that Earth-Moon distance, 3.84 times 10 to the 8. Subtract that 4.67 times 10 to the 6 meters. And what you end up getting is 3.79 times 10 to the 8 meters. So yeah, it's much further away from the barycenter, which is what you'd expect. Okay, so now I have that information. Both of these bodies are orbiting, so both the Earth and the Moon are going to be orbiting this barycenter at the same rate. In other words, the period is going to be the same. So if their period is going to be equal to, I know V equals 2 pi T, right? So I know the period is equal to 2 pi R on V. So that would mean if their periods are the same, 2 pi R E on VE is going to be equal to 2 pi R for the moon on the velocity of the moon. And the 2 pi's cancel out. So I'm looking at a ratio of their radii pretty much. So it's asking to show what the velocity of the moon is. So I'm going to isolate this part by itself, and it ends up being RM on RE VE. And if you sub those values in, what you end up getting is 81.2 VE. So you're showing that the velocity of the moon is roughly 81 times the velocity of the Earth. And that is the exam done.